Hopefully most of you have already gotten through a lot of that. If you haven't, you should probably start on that right away. It's due this evening at 11:59 p.m., submitted via Gradescope. If you are late, our late policy, as I mentioned in the beginning, is that you have 5 late days cumulative over the whole course. Please don't use them all up on the first homework assignment. You'll probably need them later. So don't be late. And remember to start forming your final project groups. So September 25th, your final project proposal is due. You may, of course, modify your project plan after that, but it's a good idea to get something very kind of plausible in place for your final project proposal, because that's your opportunity to get feedback from us, from the course staff, and also from your peers about whether your project proposal idea really kind of makes sense and how you could improve it. Okay, today's lecture. So today we're going to talk about the policy gradient algorithm. The policy gradient algorithm is essentially gradient descent or gradient ascent for reinforcement learning. It is in some sense the most basic of reinforcement learning algorithms. We're going to talk about what the policy gradient actually does. We'll talk about some ways to make the policy gradient actually work. For example, by exploiting the fact that the future doesn't cause the past. That turns out to be a very important fact in our universe that makes policy gradients work a lot better. We'll talk about these things called baselines that are also really important to make policy gradients work better, and a few other details. And then at the end, we'll go through some examples of policy gradients in action, learn about the names of some commonly used algorithms, and then we'll have a little reading list at the end for those of you that want to dive into more depth about some of these topics. We'll actually have another lecture on more advanced policy gradient topics much later on in the course, but this lecture will cover all the material that you need for homework 2. So the goals for today's lecture: understand policy gradient reinforcement learning, understand some practical considerations for policy gradients. So policy gradient, like many reinforcement learning algorithms, is one of those methods where kind of the textbook version really doesn't work, and in order to make it really work, you need to know a bunch of details. And this will be something you'll see again and again with deep RL methods. So in the first half of the lecture, we'll present kind of the textbook version. In the second half of the lecture, we'll talk about how to make it actually work for real. All right, so let's recap very briefly some of the things we discussed last week. So last week we saw that we could formulate an objective function for reinforcement learning. And to formulate this objective function, we went through the following kind of thought process. What we're after is a policy. Later on, we'll find out how we could actually do RL where we don't represent the policy explicitly, but for now, let's just say that the policy is represented explicitly by a model, and this model is some kind of function approximator. In deep RL, it will often be a deep neural network, but it doesn't have to be. And this function approximator outputs the parameters of a conditional distribution over the actions conditioned on the input, which for now we'll just say is the state, although it could also be the observations. So for now, we'll just stick with a fully observed case. We'll mention some special considerations for partially observed RL in the middle of today's lecture. So the reason that I write pi subscript theta is that the theta refers to the parameters of this function approximator, which for a deep neural net corresponds to the weights of the network. So the weights at every one of these layers. The state goes in as an input, the action comes out as an output sampled from that distribution, and then the state and the action together gets sent to the environment, the universe, which picks the next state from the unknown transition distribution. So this P of S prime given S comma A, this is basically kind of a laws of physics that govern this universe. Out comes the next state, and it goes back into the policy. We can write out this stochastic process mathematically. It basically provides a distribution over a sequence of states and actions, which we refer to as a trajectory. And that distribution is factorized into a big product. That product involves the initial state distribution, which in general we assume is unknown, the transition distribution, which we also assume is unknown, and our policy, which is the only part of this that we actually get to pick. As notational shorthand, if you see me write P subscript theta of tau, that is referring to this distribution over trajectories, and the reason that it has a subscript theta is, of course, because it is influenced by the policy. So tau is just a shorthand that I'm going to use for S1, A1, S2, A2, etc., up until S capital T, A capital T. So last week, we saw that once we define the trajectory distribution in this way, we can use it to actually define an objective that we would like to optimize, and that objective defines the reinforcement learning problem. So here is the objective. The objective is the expected value under this trajectory distribution of the total reward along that trajectory. So if your reward is, let's say, +1 if you're driving happily on the road, -1 if you go off the cliff, what you would like to do is you would like to maximize the cumulative reward over the entire trajectory of your existence. We saw last week that we could formulate an infinite horizon version of this as well, so we could formulate a variant on this objective as we take capital T to infinity. We won't deal with that today, but we will see more of that later. For now, let's just stick to the more convenient and simple finite horizon case. Okay, so this is all a recap from last week. All right, so now let's talk about how we can actually optimize this objective, how we can maximize the expected value of the total reward under the trajectory distribution induced by the policy pi theta. Before we actually get into the whole maximization thing, let's try to think about something even more basic. How do we even evaluate this objective? How do we obtain an estimate of this expected value? If we do not know the transition distribution, we do not know the initial state distribution, we just have the world to interact with and our policy. Any ideas about how we can obtain an estimate for this expected value? Yes?
You take samples from the environment by interacting with them?
Right. So one of the ways that you can estimate an expectation is that you can generate samples from the distribution under which the expectation is taken, and then average together the values of the quantity inside the expectation over those samples. So the distribution is p theta of tau. The quantity of interest is the sum of the rewards over the trajectories. So one of the ways you can estimate that expectation is to obtain samples from p theta of tau. And the way that you can obtain those samples is by actually using your policy to act in the world. So if your policy controls a car driving on that cliff, just drive the car 50 times, average the total reward over those 50 trials, and that's your estimate of the expected value of the total reward. It's a very simple way to obtain an estimate of an expected value, and we'll actually use this sampling-based estimator multiple times in today's lecture, not just to obtain the value for the objective, but also to actually figure out how to improve it. So for notational convenience, if you see me write j of theta, that's just referring to this whole expectation. So j of theta is basically the objective of reinforcement learning as a function of the policy parameters theta. So j of theta is equal to this expectation, and I can approximate it using samples. So when you see me write an equation like this, that just means I drew capital N samples, and I'm summing over all those samples of the quantity inside the expectation, which is the sum over time of the reward. So you generate some samples, evaluate the total reward of each of those sample trajectories by summing together the rewards along all the time steps in those trajectories. So maybe the green one is the best one, the red one is the worst one, and the orange one is somewhere in the middle. Average those together, and that gives you an unbiased estimate of the expected reward of your policy. Yes?
What's I again, the index?
The subscript I indexes over the samples. So this sum over I is from I equals 1 to capital N. Okay, so that lets us evaluate the objective. Now let's talk about actually trying to maximize that objective. So hopefully from your machine learning course, all of you know that if you can calculate a gradient, then you can take a step in the direction of that gradient to increase the function value, take a step in the direction of the negative gradient to decrease the function value. Since we are using rewards, we'd like to maximize it. If we had costs, we would minimize it. So here, since we want to maximize the quantity, what we want to do is calculate the gradient and take a step in the direction of the gradient. So for notational convenience, again, if you see me write some p theta or pi theta, that denotes the distribution over trajectories. Unfortunately, my slides are a little inconsistent. P theta tau and pi theta tau mean exactly the same thing, so don't worry about that. I'll fix those for next year. And r of tau is just shorthand for the total reward over the trajectory tau. So if you see something of tau, that just denotes the sum in the case of rewards or the product in the case of distributions. Okay, so we can write out an expectation like this as an integral of the probability of that trajectory times the reward of that trajectory. And now if we want to calculate the derivative, we're going to try to differentiate this thing. So j of theta is equal to this integral. So for the derivative, since integrals are linear and I can put the gradient operator inside of it, what I really want is the gradient with respect to theta of pi theta of tau times r of tau. Now this quantity might at first seem a little daunting to obtain because pi theta tau contains inside of it the unknown initial state distribution and the unknown transition distribution. So we need to do a little bit of calculus magic to really get this quantity. And there's a very convenient identity that we can exploit that makes this very straightforward to get. So this is the identity. If you have a quantity like this, pi theta tau times grad log pi theta tau, then you can look up the equation for the derivative of a logarithm in a calculus textbook and find out that the derivative of a logarithm can be written as the derivative of the quantity that you're taking the logarithm of, which is pi theta tau, divided by that quantity, which is pi theta tau. So pi theta tau grad log pi theta tau can be written as pi theta tau grad pi theta tau divided by pi theta tau. And that's quite nice because now the denominator here cancels with this quantity and you're just left with grad pi theta tau. So grad pi theta tau is what we've got over here. So we can substitute the left-hand side of this equation and turn that integral into the integral over tau of pi theta tau grad log pi theta tau times r of tau. And this is now very, very convenient for us because this integral has a pi theta tau in front of it, which means that it can also be written out as an expectation. So the derivative of j theta can be written again as an expectation with respect to pi theta tau of grad log pi times r. Okay, now we're not quite out of the woods yet because we still need to figure out what this grad log pi actually is equal to. So let's work on that a little bit. So here we're going to bring back our equation for the distribution over trajectories. So this is the pi theta tau, and this is what it's equal to. And because we're after grad log pi theta tau, I'll take the logarithm of both sides. Now when you take the logarithm of a product, you get a sum of logarithms. So if I take the log of both sides, I get log pi theta tau is equal to this huge thing. But this huge thing basically consists of three types of terms: log initial state distributions, log transition probabilities, and log policy probabilities. So let's take that whole thing and substitute that in there for our log pi theta tau. And now remember that we're trying to take the gradient of this whole thing. So we don't really care about this quantity, we care about the gradient of this quantity. And of course, because we have a sum, we can push the gradient operator inside the sum. So can anybody tell me what grad theta log p of S1 is equal to? 0. Yeah, it's equal to 0 because theta does not affect the probability of starting an initial state. Regardless of which policy I pick, the universe will not change how it picks initial states for me. What is the derivative with respect to theta of log p of st plus 1 given st at? 0, yeah. So regardless of how you choose to buy or not buy lottery tickets, the probability of winning the lottery is not altered by your policy. That's determined by the universe. So random transitions are unaffected by theta, initial state probabilities are not affected by theta. So both of these cancel out, and we're just left with the log pi theta terms, which conveniently enough are actually the only terms in this sum that we know, because that's our policy. So we can rewrite the gradient of the policy like this, removing all the terms that whose derivative is 0, and leaving just the grad theta log pi theta terms. And now we have something very, very convenient because we have a bunch of terms here which we can evaluate because the policy is actually known to us. We have a bunch of rewards here that we can evaluate, and all of this is taken in expectation under pi theta tau. So now, could anybody tell me how we can estimate this policy gradient? Please raise your hand and provide a description. It's going to be very similar to how we evaluated the objective value before. Yes?
Again, we
sample trajectories, sample n trajectories, and then just evaluate our policy on those and evaluate our reward function on those, and we can just sum them up. And,
right.
Yeah.
Precisely. So just like before, we evaluated our reinforcement learning objective value by generating samples, by actually running our policy in the world to get an estimate of an expectation of this form. Now we'll do exactly the same thing, only on those samples we won't just sum together and average the rewards. We'll sum together the rewards and sum together these grad log pi's, multiply them, and then average that. So in order to evaluate the policy gradient, we basically use the same idea as before, using samples. So we generate some samples, evaluate their rewards, also evaluate their grad log pi's, and then average those together. So this is an equation that we can actually implement in a computer to estimate the policy gradient using n samples. And then once we've evaluated the gradient, then all we do is we modify our parameter values by taking the old parameters plus some learning rate times the gradient, and that implements gradient ascent. In practice, of course, you can use other more powerful optimizers, but this is kind of the basic version that we'll go through in the first half of today's lecture. Yes, question?
How do you know how big n should be, and is it related to t?
Right. Yeah, so the question is, how do we pick capital N, and is it somehow related to the horizon capital T? So the answer is that in practice, we always choose n heuristically. We'll discuss some rules of thumb for how to choose n. As a hint, it needs to be a bit bigger than what you're used to in deep learning. In terms of the theory, there is some variance analysis that can be done that relates capital N to capital T. We won't cover it in this class because I didn't prepare for it in this lecture, but there is some reference on that, and we could discuss that afterwards. Yes?
How do you make sure that the trajectories you get match the probabilities of the expectation? Like the empirical
Right.
frequencies of
Good, good. So the question was, how do you make sure that the trajectories you get actually match the probabilities that you want, right? Because you want this expectation to be under pi theta t. So the answer is that if you actually run your policy, the assumption in reinforcement learning is that the process that generates that trajectory matches that distribution. So when you basically request the environment, please let me run my policy, it'll put you in a state sampled from P of S1. Then you pick the first action from your policy, and then you assume that the environment will then generate a sample from P of S2 given S1 comma A1. If this is not true, then basically this isn't going to work. We will discuss what happens if you have samples from other distributions later on, though. There are a few tricks there. Any other questions? Yes?
Why is the reward of tau not dependent on theta?
Why is the reward of tau not dependent on theta? Good question. So remember that the policy is actually a probability distribution. So the policy doesn't just give you one specific action for every state. It actually gives you a probability distribution over actions given states. Once you've actually sampled those actions, you have states and actions, you can plug those into the reward. The reward only depends on the states and actions. So if you alter the probability of the actions, then the expected reward will change. And that's actually already accounted for by these gradient terms out front. Another way to think about this is if you think back to the lecture from last week when I talked about how non-smooth functions can still have smooth expectations. This is basically the same thing. So the example I had last week with falling off the cliff versus not falling, where there was a probability of the falling action that was given by theta. If you go back to the slides from last week, you'll see that there the equation for the reward was theta times reward for falling plus 1 minus theta times reward for not falling. So even though the reward was not smooth, the whole expectation was smooth in theta. There's a question here.
How do you calculate the log gradient with your samples?
I'll come back to that. Yeah. Yes?
It seems like all of this is built on the fact that the environment is Markovian. So are there any modifications you would do, if say you have an environment where an action 10 steps ago would affect the current state?
Yes, we'll come back to that. We'll actually talk about partial observability, and then I will ask you whether it works, and then you can explain it to me. Any other questions? All right. So let's, just to kind of round out our discussion of this algorithm and to really solidify that, let's come back to the anatomy of a reinforcement learning algorithm. So last week I talked about how every reinforcement learning algorithm consists of 3 parts: generation of samples, fitting a model or estimating a return, and improving the policy. And this algorithm does do all 3 of those things. So the orange box is when you sample from your policy to get those samples from pi theta tau. The model here is very, very simple. The model just amounts to summing together your rewards. Later on, we'll actually see that we can replace this sum with more sophisticated estimators. So right now, the green box is basically a summation operator. Later on, we'll see that we can use more fancy neural network learning methods to replace this piece. And then the blue box, the part where you actually improve your policy, is just this gradient ascent line. So you just take your gradient and take a step in the direction of your gradient, and that improves your policy. As soon as you do that, of course, you need to generate more samples. So using this derivation, we can actually already describe one of the most basic reinforcement learning algorithms, which appropriately enough is called reinforce, which is some complicated acronym that I don't remember. But the way that the reinforce algorithm works is that you sample a set of trajectories from your policy by literally running that policy in the environment. Then you estimate the policy gradient using those samples, basically using this equation up here. And then you take a gradient step in the direction of that gradient, which improves your policy. So this is the reinforce algorithm. If someone says, I train my policy with reinforce, this is what they mean. Only not really, because if you actually code this up, it won't work. So what we're going to talk about from here on out is how to actually make it work. But first, we'll get a little bit more in-depth understanding of what it's doing. Yes? We'll find out.
Okay.
So stick around for the second half to find out the surprise ending to this story. But before we find out why it doesn't work, let's try to understand it a little bit better. Okay, so first, what is this thing? What is grad log pi? And if we understand what grad log pi is, maybe that can help us implement it. So let's think of a kind of a practical example. Maybe we have our driving policy. So images go in, steering commands come out, and we have a pi theta of a given s. If we have a discrete action space, maybe it's just like turn left, turn right, or drive straight, then we might implement pi theta a given s as a neural net that outputs the logits for a categorical distribution. Then you have a softmax layer on top, and that basically gives you probabilities over the three actions. So that's a very standard design that you could use, for example, for a neural network classifier, and that basically implements pi theta a given s. So then the gradients of the log probabilities will just be obtained directly from your automatic differentiation software. It's a bit kind of, for me at least, it's kind of illustrative to consider how this compares to standard supervised learning. So when we do supervised learning, we're really doing maximum likelihood estimation. So the objective for maximum likelihood estimation, kind of the supervised learning setup that we had before, its gradient can be written out like this, right? So the gradient for maximum likelihood is just the sum over all your samples. I'll assume that my samples are arranged into trajectories, so I also have a sum over time steps, and in there I have the gradient of the log probability of the action that was taken in the data given the state that was in the data. So this is just supervised learning, maximum likelihood. And if you look at that, and then you look at the policy gradient, you'll see that they're actually quite similar, except that the policy gradient multiplies those grad log pi's by these total rewards. And this is actually quite a useful fact to know, because when we actually go to implement the policy gradient, we can implement it in a very similar way as how we implement maximum likelihood training. Let's go through another example. This was for continuous actions. So you could imagine using policy gradient to train a little simulated robot, in this case, to run around. Now this simulated robot is going to have continuous actions, not discrete actions. So we need pi theta a given s to define a distribution over some continuous value. A very popular choice is to use a multivariate normal distribution. So in a multivariate normal distribution, your policy is, maybe its mean is defined by some neural network. Its covariance might also be defined by some neural network, but for now I'll just say the covariance is constant for simplicity. And theta represents the parameters of this neural network. So if you write out the log probability, this is just the equation for the log probability of a normal distribution, where everything that doesn't depend on the mean I've just kind of wrapped into this constant over here. So all the bits that depend on the neural network f are just this piece. Very simple equation. And if you take the derivative of that with respect to theta, this is basically the equation you get. So you can work this out on paper at home. Hopefully I didn't make a mistake. This is the grad log pi theta for a multivariate normal distribution, where the mean is parameterized by this function f. Okay? Now, of course, you don't actually have to do this by hand typically. If you use automatic differentiation software like TensorFlow or PyTorch, it'll do this calculation for you. But this is just to kind of make it more concrete and to see that there's a relatively simple equation you can derive for these things in terms of the derivatives of some deterministic function. Any questions about this?
What's the norm subscript covariance mean? Is that like the quadratic form or something?
Yeah, exactly. So this is just the quadratic form in sigma inverse. Yeah, this is just literally like the Wikipedia equation for the multivariate normal distribution. Okay, so that's kind of the mathematics of it. But let's talk also a little bit about the intuition of what's going on here. It sort of seemed like we did a bunch of math magic. We ended up with some funny formulas. Those funny formulas implement gradient ascent. But what did we really do? Like, how does this algorithm actually change the policy in practice? So this is our policy gradient. And just looking at the form of this equation, you can kind of maybe imagine that what it's going to do is it's going to take the gradient. So the gradient of log pi tau basically points in the direction that will increase the probability of the trajectory tau. So if I change my parameters in the direction of grad log pi tau I for a specific trajectory tau I will make tau I more probable. So if I multiply those gradients by r tau I, it kind of seems like what I'm doing is I'm making the high reward trajectories more probable and the low reward trajectories less probable. So compared to the maximum likelihood gradient, which just makes everything more probable, right? Maximum likelihood just takes all of your data and just makes it more likely. This one multiplies it by r tau, which means that things with bad rewards will actually be made less likely. So you can imagine it visually like this. You have your trajectories. You evaluate their rewards. Some of them are good, some of them are bad, some of them are in the middle. Your policy induces a distribution over trajectories. So if you got those three trajectories, maybe this height field represents your distribution, you'll take the ones with the good rewards and you'll increase their probabilities, take the ones with the bad rewards and decrease their probabilities, and this will make the expected reward larger because the good stuff got more likely, the bad stuff got less likely. So good stuff is more likely, bad stuff less likely. This is essentially just a very fancy mathematical version to formalize trial and error learning. If you got it right, do it more often. If you got it wrong, do it less often. So this is basically the intuition behind this method. Any questions about this? Okay. Now let's come back to this partial observability point. Here I'm going to ask a pop quiz. Can I do policy gradient with partial observability? Raise your hand if you think that this is allowed, without any changes to the algorithm. Raise your hand high. OK, good. It's OK to guess. Now raise your hand if you think it is not allowed. OK, so could somebody who thinks that it is not allowed give me an explanation? Could somebody who, yes?
The policy assumes that like actions are independent, so like the action you take in one state won't affect possible actions that you take in another state, but that's not true because like if you like actions affect actions, it's still like.
OK, so that's a reasonable hypothesis, right? Actions affect other actions. Could somebody who thinks that it is allowed tell me why that's the case? Yes.
Because while we only have partial observability, we're still asking a world which does like have God abilities and knows everything to actually tell us what the next transition will be. So we still maintain our transition probabilities even though we don't necessarily know the full state. So then in expectation, it should still end up being about average.
Yeah, I think that's a reasonable way of looking at it. So the way that I look at it is that if you actually write out the equation like this, the assumption that the policy pi is conditioned on the Markovian state is not actually used anywhere by the policy. So the policy is just some function approximator that looks at something and outputs an action distribution. And nowhere in this derivation did we ever actually assume that the thing that the policy is conditioned on actually obeys the Markov property. Now, underneath all this, there needs to be some system that obeys the Markov property, but we don't need to know what that system is. We just need to observe samples from that and get rewards. The policy can be conditioned on whatever the heck we want. And of course, any system can be turned into a Markovian system if you just define your state as the full history of all observations you've seen so far. So, that might not be a very satisfying way to turn it into a Markovian system, but we don't care because we never even need to know what the state is. All we need to do is to be able to generate samples, get reward values for those samples, and evaluate our log pi's, which can be conditioned on whatever we want. So that's kind of a convenient fact with policy gradient, that essentially we can just completely ignore all this stuff and just do it on partial observability. This is the only algorithm that I'm going to cover over the next few weeks for which this is true. Once we start introducing value functions, this will no longer be true. There's a question over there?
Yeah, so when you replace your states with your observations in that equation, why doesn't that mess with your sampler at the front? Because doesn't 1 over n times the sum from I equals 1 to n require some independence of the observations to be a valid estimator?
So the sampler is still assumed to sample states under the hood. Like basically, it's sort of, this is not even an assumption about what's in your code. This is an assumption about how the universe works, that when your policy interacts with the environment, that environment has a state, and it generates samples of those states. But then what it shows you is the observations that are given rise according to those states. So you never actually see the states, you never know what they are, but they do exist there somewhere. And the nice thing is that any process, no matter how non-Markovian it is, can be written as a consequence of some underlying Markovian process, defined in a very trivial way, just by setting the states to be the concatenation of observation histories. Yes?
Why does our reward function still take in the state when we don't know what the state is?
Right. So I was wondering if anyone would catch me on this. So this thing, this R, still takes in S. And this is a little bit of a delicate point. So the actual assumption when an algorithm like this is implemented is that the environment will give you your observations and will actually also give you reward values. Not reward functions, just actual reward values. And those values do actually need to depend on states, but if they depend on observations, you can equivalently just assume that your rewards are stochastic, right? Because observations are a stochastic consequence of your states, so you can say that a function of the observations is just a stochastic consequence of your states, and then you're just assuming you don't observe deterministic reward values, but stochastic reward values. And with stochastic reward values, you get another little expectation in there, and all the math still works out. Yes?
Is there any type of model that estimates the emission probabilities?
Right, so the question was, are there methods that actually explicitly estimate emission probabilities? Absolutely, and we'll talk about those in 3 or 4 weeks when we talk about model-based RL. Okay, let's continue. So now I kind of alluded to this before, that if you actually code up reinforce the way I described, it won't work. So what's wrong with policy gradient? I'll tell you about a few things that are wrong. I'll start with something that's maybe one of the simpler issues to kind of motivate what will come next. So let's say that I have a Gaussian policy, and I'm going to draw this kind of cartoony picture where the x-axis is the trajectory. Now, trajectories are not usually one-dimensional, but pretend that it's like some one-dimensional projection. And the vertical axis, I'm going to overload it to mean both probabilities and rewards. So that blue curve represents my Gaussian policy. And let's say that I observed 3 samples. And 2 of those samples had rewards that were small positive numbers, and 1 sample had a reward that was a very negative number. Now, if I use those 3 samples to estimate my policy gradient, you might expect that my policy will kind of slide over to the right a little bit. It'll somewhat increase the probability on these 2 samples and greatly decrease the probability on this sample, right? Because this sample is a big negative number, so it really wants to drive that to a very, very low probability. Now let's say that I took that same exact reward function and I added a big constant to it. So then my samples would be these yellow lines. The relative rewards are exactly the same. All I did is I added a constant. Adding a constant doesn't actually change which policy is good or bad, because the constant affects all policies equally. But the policy gradient obtained from these rewards will be very different, because now the policy is trying to make this more probable and this even more probable. So it'll actually spread out a little bit to cover all 3 of those things. And this should be very weird to us, because we haven't actually changed the problem. We just added a constant to the objective function, and suddenly our gradient estimate does something totally different. As a thought exercise, what if the two good samples, these two over here, actually have a reward of 0? So what if I were to choose the constant such that these two drive down to 0 and this one becomes a big negative number? What might happen then? Well, the disturbing thing then is that the direction that the policy goes depends entirely on whether it starts off on the left side or the right side of this bad sample. If it starts off on the left, it'll actually run away from the good stuff. If it starts off on the right, it'll go towards it. This is a kind of one illustrative example of to explain how the policy gradient has high variance, meaning that when you get different samples, you get very different gradient estimates from those different samples. So for a small finite number of samples, you might get very different policy gradients if you test multiple sample batches. And this is a big problem because in effect it means that your gradient is very noisy. So if you estimate your gradient with a modest number of samples, you won't go straight to the optimum, you'll take a really zigzag path, and for too large of a learning rate, you might never get there. And this is a really, really big problem for using the policy gradient in practice. So on that note, I'll briefly recap what I covered in the first half of the lecture, then we can take a break. During the break, you guys can come up and ask questions, and after the break, I'll tell you how to fix this damn thing. So to review, evaluating the reinforcement learning objective, generate samples, average together sampled rewards. Evaluating the policy gradient, generate samples, use the log gradient trick, and average together the rewards multiplied by the grad log pi's. Understanding the policy gradient. It's essentially a formalization of trial and error learning. It makes the good stuff more likely and the bad stuff less likely. Partial observability, don't worry about it, it just works. What's wrong with policy gradient? It has high variance, and that's what we're going to try to fix after the break. So let's take 3 minutes. We'll come back when that clock hits 10:50, and feel free to come up and ask questions if you'd like during the break.
So I guess it's more like a notational question. So is pi theta just like the probability of like taking action A like in state S A?
So you're referring to
like the log pi theta thing, basically.
This thing?
Yeah.
Yeah. So it's just a probability. So your neural net outputs typically, if you have like, you know, state S goes into your neural net, it outputs A. What it's really outputting is a number for every action. If you have a softmax at the end of your neural net, those numbers sum to 1 and they're all positive.
Okay.
So those represent the probabilities.
Oh yeah. So I guess that point is like we're saying the policy is stochastic, right? Like, it's not deterministic.
Yes.
Okay.
It's still sort of related to the sampling question I asked.
Yep.
Basically because when we do, sorry my writing is terrible,
it's okay.
Like when you do this, when you have this expectation here that we're approximating with the sampler, this is over pi theta of S comma A, right? And so if this is pi theta of O comma A, isn't there going to be some kind of difference between the distribution of stuff you get from your sample?
Yeah. So there, I mean, the actual derivation, okay, so I guess what I should have said is the algorithm stays the same, the derivation changes. So obviously the derivation needs to have an expectation, I guess it'll take me a while to write out. The derivation needs to have an expectation over O.
Right.
So actually, now your process is like P of OT given ST, pi of AT given OT, and then like P of ST plus 1 given STAT. And this whole thing is a product over T, right? But these you sample from at the same time as you sample from these. So the universe samples an X state and then samples an O for it.
All right, fair enough.
I have a question about the formula.
Okay.
The very beginning,
Which formula?
At the beginning of the product, like you're saying.
You can look that up there.
Thank you.
Can you tell me which formula it is?
I think it's at the very beginning. Like I saw that formula for many times, and I think like.
You mean the objective?
Yeah. I think that means this one.
This one?
No. This one?
Okay. Yes, the trajectory distribution.
I think you mean ST plus 1. Because when you take T equal to big T.
Oh yeah, it's off by 1, right? Yeah. So people actually do this in a few different ways. So you can either assume that your trajectory is let's say you have a length 3 trajectory. You can either say that it's S1, A1, S2, A2, S3, or you can say that there's an action at the end. And this is like, you can pick, either you want this or you don't. So it depends on whether you want your trajectory to end in a state or end in an action. Because people sometimes say it should end in a state because it doesn't matter what action you take at the very end. But it's like a design choice.
Oh, I see. So like the formula here, I mean, like this looks not very the same as this.
Yeah, you're right. So here I should have put like an S capital T plus 1 at the end. Yeah, you're right. Okay, I need to resume, but I'll be happy to take any more questions afterwards. All right, we're going to resume, so please find a seat. So before the break, we left on a cliffhanger that policy gradients have this big problem. And now after the break, we'll try to resolve that problem. So we'll talk about reducing variance in policy gradients. The first method that we'll use to reduce variance is going to be by exploiting the fact that our universe has causality, meaning that the past influences the future, but the future does not influence the past. So, this is something that's been true throughout all of my life, hopefully something that's been true throughout all of your life too, and maybe we can assume that that's just a truth of our world that always holds. Turns out that this particular truth can allow us to get a lower variance policy gradient. Why is that? Well, the variance of some quantity is intuitively that the variance is bigger if the quantity is bigger, the variance is smaller if the quantity is smaller. So if I were to take all of these rewards and make them 10 times smaller, numerically the variance would also be smaller. That's maybe not super satisfying, but let's see what happens when we make use of causality. So more formally here we can say that it means that the policy at time t prime cannot affect the reward at time t when t is less than t prime. So what you do tomorrow is not going to change what grade you get on the homework tonight, right? Because tomorrow it'll be too late. Unless you take a late day. So here's how we can use that. We can take this sum and we can distribute it inside the sum over the log pi's. So what I wrote here is just exactly the same as up here. I just used the distributive property to distribute this sum inside of this sum. So now I have an outer sum over all the time steps of the grad log pi times an inner sum over t prime from 1 to capital T. And now, here I can actually make use of causality, because here I have the grad log probability of the action at time t, but it's being multiplied by a bunch of rewards that include rewards that happen after t and rewards that happen before t. But I know that the action that I take at time step t cannot affect the reward at some other step t prime that happened prior to that. So what I can do is I can actually make use of this fact to change this sum. And what I'm going to do is I'm going to change this number, this 1, to a t. I'm going to say, when we multiply grad log pi at some time step t, let's only multiply it by the rewards that we get at that time step and later, rather than all of the earlier rewards, because it can't affect the earlier rewards. It turns out that this is still an unbiased estimator for the policy gradient, and I'll actually have a paper reference at the end of this lecture if you want to read more about that. But the intuition behind it is that it's basically making use of the fact that the action you choose now will not affect the rewards that you got in the past. And the reason that this reduces your variance is that now you're multiplying these grad log pi's by numbers, by sums, that are smaller, because you're not adding in all those older rewards. So simply by the fact that these sums are now smaller numbers, the overall variance of the policy gradient actually goes down. And in practice, this little trick is very, very useful for reducing the variance of the policy gradient and tends to make it work quite a lot better. In fact, it makes it work so much better that you will often see standard derivations of policy gradient that say that don't look like this, but instead they use the term reward to go, often denoted with q hat, and they're written like this. They just say grad log pi times the reward to go. And that reward to go, hiding inside of there, is that sum from time step t until the end, representing the total reward that you'll get from that time step until the end of time. So this is the actual, kind of the more realistic form of the policy gradient that you'll often see written out and that you'll often see actually implemented, because there's basically no benefit to adding in those rewards from previous time steps. Your current action cannot affect them, and they only serve to increase the variance. Any questions about this? Yes?
Is there any way to show that these are equivalent?
Yeah, so I'll have a paper reference at the end by Baxter and Bartlett, and that paper goes into more detail about it. Going through that proof will take me a little too much time in today's lecture. Any other questions? Okay, so that's just a neat little trick that basically you should always do because it never hurts and only helps. There's another trick that never hurts and only helps, but it's a little bit more involved, and this one we will actually go into in a bit more detail, and that's the baseline. So before, if you remember, we had this intuition about how the policy gradient works, that it makes the good stuff more likely and the bad stuff less likely. And that was very natural and very appealing, but it's not really true, right? Imagine that all of my rewards are like on the order of 1 million, and the good stuff is 1,000,001, and the bad stuff is 1,000,000 minus 1. Now, the R's are all about 1 million, so everything is getting more likely, both the good stuff and the bad stuff. So intuitively, what I would like to do is I'd like to take the things that are better than average and make those more likely, and take the stuff that is worse than average and make that less likely. Does anybody have any ideas about a simple modification to this formula that would effectively implement that? Yeah.
Just take RT minus like average reward.
Yeah. Like what if we just do that? Just take R of tau and subtract the average reward over the samples. So instead of multiplying grad log pi by the total reward of that trajectory, multiply it by how much better that trajectory is than average. That kind of seems very natural. It seems right. Like it seems like it actually implements trial and error learning. But are we actually allowed to do that? Like, is that mathematically correct? Well, it turns out that actually, in expectation, this quantity is the same as the one that we had before, but has lower variance. How are we going to prove that? Well, we're going to analyze this new term that we've added, right? So all we've done, we can use again the distributive property and show this grad log pi times r minus grad log pi times b. And let's analyze this grad log pi times b term, right? We have an expectation over tau on the outside. What is the expectation of grad log pi times b? So whenever you have an expectation, you want to know what it means, write out the actual integral or sum. So we have this integral pi tau, grad log pi tau b. And now we'll go back to our convenient identity, and we'll actually apply it in reverse. So before we had to unpack the gradient, take out that log, and take out that pi. Now we're going to pack it back up to take our pi times grad log pi and pack it back into a grad pi. So now we have grad pi times b. Now remember, the gradient operator commutes with the integration operator, so we can take the b on the outside, and we can take the grad on the outside. So we have b times the gradient of the integral over tau of pi tau. Can someone tell me what this integral is equal to? 1. Yeah, if you integrate a probability distribution, you get 1, unless you made a coding mistake. So if you implemented it correctly, you should get 1. And the gradient of 1, very easy to calculate. You don't need a calculus textbook for that. That's just 0. So b times grad 1 is 0, which means this whole thing on the left is 0, which means that you can subtract any constant you want, and you will not change the expected policy gradient. Question?
Maybe it's a basic question. Like, why do we need the term b again?
Why do we need b?
Yeah.
So the intuition is you need b so that the good stuff becomes more likely and the bad stuff becomes less likely. The formal reason will be shown on the next slide. Okay, so subtracting any b you want will not change the expectation of the policy gradient. It will, however, change the variance, right? So the expectation is the first moment. The first moment is unaffected. The second moment actually is affected. There was a question?
Yeah, on the same, like this is bordering on like widening our data. So would it also be a good case to then not only just center
Yes.
our reward, but also to, yeah.
It's a very good idea.
Okay.
If I have time at the end of today's lecture, I'll cover it, and if I don't, I'll cover it in the advanced policy gradient lecture. Yeah, so hold that thought. All right, so subtracting baselines is unbiased in expectation. It has this nice intuition that it actually increases the probability of things that are better than average, decreases the probability of things that are worse than average. So is there a mathematical reason, a more formal reason why this is desirable? Well, what we're going to do on the next slide is we're going to actually derive the optimal baseline. I'll tell you right now, the average reward is not the optimal baseline, but it's pretty good. And if you want to implement a baseline in practice, use average reward. But if you want to do a bunch of math, then stay with me for the next part. So let's do a bunch of math. So subtracting a bias does not change the first moment. It does not change the expected policy gradient. It does, however, change the variance. So let's try to figure out what that is. You can open up a textbook, look up the equation for variance. When I did that last night, here's the equation I found. Hopefully you'll find the same equation. And you can just substitute that in. You can take the thing that we want, which is our policy gradient, plug that in there. And what we're going to try to do here is we're going to try to write out the variance of the policy gradient, and then we'll take the derivative of the variance with respect to the baseline b, set that derivative to 0, and figure out what the optimal baseline is. So let's go on that journey. This is the thing that we're going to plug in for x. So let's plug that in. So here all I've done is I've substituted this in here. So the variance of my policy gradient is the expectation under pi theta of tau of the stuff inside the expectation squared minus the whole expectation with a square on the outside. Now for that second term, I've already told you that the expectation with the b subtracted is exactly the same as the original expectation. That was what I proved on the previous slide. So this second term, its derivative with respect to b is going to go to 0 because it doesn't depend on b. So this bit is just the expectation. Squaring it doesn't do anything, so in terms of its dependence on b, so I can just ignore that second term if I want to analyze the effect of b on the variance. So it's really only the first term that matters. So I'm going to change my notation a little bit so that this is a little bit less cluttered. I'll use g of tau to denote grad theta log pi theta tau. So when you see g of tau, that's just this bit up here, just to make it shorter. And now I'm going to expand it. I'm going to take that square, I'm going to distribute it inside, and then I'll distribute the square inside this difference. And I'm going to be taking the derivative of this whole thing with respect to b. So when I distribute the square, I of course get 3 terms. So I have d db of the expectation of g squared r squared minus 2 times the expectation of g squared rb plus b squared times the expectation of g squared. Okay, that's just, you have one number minus another number squared, distribute the square inside, you get 3 terms. So these are the terms that you get. So now let's look at the derivative of each of these 3 terms with respect to b. For the first one, it's 0, right, because there's no b in there. For the second one, it's linear in b, so it's just minus 2 expectation of g squared r. And for the third one, it's 2 times b expected value of g squared. Okay? And I'm going to set this derivative to 0 because I want to find the optimal b. So when I set it to 0, I just have to throw this negative term on the right-hand side, divide by the first term, and I get an equation for b, which is the expectation of g squared r divided by the expectation of g squared. And now this thing actually looks an awful lot like expected reward, except I don't average the rewards together. I instead weight them by their squared gradient. So this is just expected reward weighted by gradient magnitudes. Now, of course, your gradient is a vector. It has more than one number in it. And if you actually evaluate this formula, b also becomes a vector. You actually get a different baseline value for every entry in your gradient, depending on the degree to which each trajectory is affected by that parameter dimension. So you actually get a per dimension baseline if you do this, which is just average reward weighted by the magnitude of the gradient for that dimension. And this is the optimal baseline. This is the baseline that actually minimizes variance. But if you want to do this in practice, my suggestion would be, when coding it up, don't bother, just use average reward. But if you want to actually know what the real answer is, this is the real answer. Any questions about this? Yes?
Why does a higher gradient magnitude, or why does weighting by gradient magnitude help?
Well, because it minimizes variance. I think if you want to get a little bit of intuition for it, it basically goes something like this, that if that particular dimension is very sensitive, then you want to basically emphasize the trajectories whose probabilities are going to be strongly affected by that dimension. So if you have some some trajectories that have very high reward, but their probability will not be changed by changing that dimension in your parameter vector, then you should not consider them in your baseline. Which kind of intuitively somewhat makes sense. But the mathematical reason is that it minimizes variance. Yeah?
If we had an oracle for B, I can see why this is the optimal, but given that we're also estimating B and that itself has variance, is still the optimal procedure?
So the question is it still optimal if you also account for the fact that your estimate of B will have error due to samples? That's a good question. I don't know the answer to that. But yeah, maybe we can discuss that afterwards. Okay, so let's briefly recap. We talked about how the policy gradient has high variance. We talked about how we can reduce its variance at essentially no cost by just not adding the stuff from the past to the sum. And we talked about baselines, which keep the policy gradient unbiased and reduce variance. And we talked about how we can analyze the variance of policy gradient and use it to derive optimal baselines. So in practice, if you want to get the simplest version of policy gradient that actually works, definitely use the average reward baseline. That thing alone will probably do the most to get your policy gradient working nicely. Then use this causality thing because it's easy and it never hurts. And at that point, you'll actually get an algorithm that can be used to solve some meaningful reinforcement learning problems. So that's sort of the most basic version of policy gradient that actually does something useful. But there's a lot more that you could do. So in the next part of today's lecture, we're going to talk about how the policy gradient is on policy and what we can do about it. So what does on policy mean? On policy means that every time you change your policy, you need to generate new samples in order to improve your policy further, and you can't reuse old samples that came from other policies. You can't even reuse old samples that came from older versions of your own policy. So why is that? Well, because the policy gradient is this expectation of grad log pi times r, and the expectation is taken under pi theta of tau. And this bit is trouble. It means that every time you want to estimate your gradient, you need to calculate a sample-wise estimate of an expectation under your current policy. If you apply that gradient and change your policy, then you cannot use those same samples to get an unbiased estimate of this expectation because your samples came from now a different distribution. So you need to generate new samples. So the reinforce algorithm, which I had before, this step 1, which is sample your trajectories from your policy, you can't just skip that step. You have to have it there. If you skip that step, then you're not getting a real policy gradient, and your policy may not improve. Now, this is a little bit of a problem when we're doing deep reinforcement learning, because neural networks typically change only a little bit with each gradient step. In general, the more nonlinear your function approximator is, the smaller the step you'll need, the less it'll change with each gradient step, which means that you might need many gradient steps, which means that for the reinforce algorithm, you might need a whole lot of samples. And if those samples are expensive, they involve, let's say, driving a real car on the edge of a cliff, you'll need an awful lot of cars in order to improve your policy substantially. On-policy learning can be extremely inefficient for this reason, but that doesn't mean that it's not useful. You might have a setting where you're using, let's say, a cheap simulator. There, it's no problem to generate tons of samples. In fact, that's going to be the case for homework 2, where we won't have you driving real cars. We'll have you driving simulated lunar landers and half cheetahs. Okay, but there is something that we can do if we want this method to be more efficient. We can actually turn policy gradient into a somewhat off-policy algorithm. This is sort of what I would call textbook off-policy. In reality, we can debate as to how off-policy it really is, but in principle, this will be an off-policy algorithm. And we'll do that using importance sampling. So what if we don't have samples from pi theta tau, and we still want to do our policy gradient? Well, we'll say that we have some samples from some other pi bar of tau instead. In practice, pi bar of tau would often be a previous version of our policy, but it doesn't have to be. It's just some other distribution. And to briefly recap for those of you that don't remember what importance sampling is a very simple, very convenient technique that we can use to estimate expectations under one distribution when we only have access to samples from a different distribution. So if I want to estimate the expectation of f of x under p of x, again, whenever you see expectation, you need to actually do some math, get rid of the expectation symbol, just write it as an integral. And now, it's very convenient in mathematics that you can always multiply something by 1 and not change its value. So that's what we're going to do. We're going to multiply it by 1, specifically by the 1 that is equal to q of x divided by q of x. And now we'll just take this little fraction symbol and we'll slide it over a little bit to write it like that. Very nice trick. And now it's an integral with a q of x out front, which means that it's an expectation under q of x. So the expectation under p of x of f of x is equal to the expectation under q of x of p of x over q of x times f of x. And that's basically the equation for importance sampling. It means that if you have samples from q of x, just multiply them by the ratio of their probabilities, then multiply them by your function value, average together your samples, and you will have an unbiased estimate of the quantity that you want. So we can plug that into policy gradient, and bam, there we have our off policy gradient. Now there's a little bit of a problem though, because these pi theta tau, pi bar of tau, they contain a bunch of stuff in there that we don't know, like p of s1, p of st plus 1 given stat, and so on. So we're not quite ready to implement this thing yet. We need to actually unpack this probability and see what it's equal to so that we can make it practical. So remember, our trajectory probabilities are given by this equation, which means that if we write out this ratio, we get this thing. So we have all the terms on the top and all the terms on the bottom. And conveniently enough, all of the things that we don't know, the p of s1 and the p of st plus 1 given stat, appear on both the top and bottom, which means that we can cancel them out. So all we're left with is a ratio of the products of the action probabilities under the new policy divided by the products of the action probabilities under the old policy. And that's actually something we can code up. That's something we can implement. So these are the actual importance weights that we have. Now, you can actually use importance sampling to derive the policy gradient in an alternate way. So we had one derivation at the beginning of the lecture. Now I'll very briefly show a slightly different derivation that uses importance sampling. And this kind of view of policy gradient will actually be useful later on in subsequent lectures also. So let's take our objective value and let's express our objective value in terms of some new parameters theta prime. So we can write out j theta prime as the expectation under pi theta, that's our old policy, of the importance sampling ratio times r of tau. And the nice thing about this equation is that theta prime only appears in the numerator of this fraction and not in the distribution with respect to which we take the expectation. So now when we go to take the gradient of this, we don't even have to worry about how we're sampling or what we're sampling from. This is the only bit that depends on theta prime. So if we write out grad theta prime of j theta prime, basically just literally take the derivative of this quantity up here, we get this. Then we apply our grad log pi trick again, the convenient identity, and we get this. And now theta prime appears in the numerator, and it appears over here, and it appears nowhere else. So if we want to use this to obtain a formula for the standard on policy gradient, that's just the special case of this equation where theta is equal to theta prime. So if we want to estimate the policy gradient locally around the current value of the parameters, which is theta, then this ratio becomes 1, and we get our old familiar policy gradient. So this is an alternative way to derive the policy gradient, starting from importance sampling without having to even to worry about how we sampled what or where. The sampling is always with respect to the old policy. But of course, we could also consider the case where theta is not equal to theta prime, and then get an actual off-policy gradient. So the off-policy gradient, the same formula, but when theta is not equal to theta prime. So now we're going to substitute in our equation for the importance weights from before, and we get this thing. So before we had two terms. We had the sum over the grad log pi's and the rewards. Now we have three terms. We've also multiplied in the importance weights. Can someone tell me, why is it a bad idea to do this? What might go wrong with this formula? The hint is, what if capital T is really big? Yes?
I guess you can drive it to 0 if you keep multiplying by a fraction or blow it up the other way.
Right. So the intuition here is that this product, you have a product of ratios that's the same as a ratio of products. So you can put the product on the top and the product on the bottom. And probabilities are numbers between 0 and 1. So when you take a very large number of numbers between 0 and 1 and you multiply them together, you get really, really small numbers. So you have a really, really small number on top and a really, really small number on the bottom. How small? Well, exponentially small, because it's on, you know, if all of your probabilities are on the order of epsilon, both the numerator and the denominator are on the order of epsilon to the power capital T. So you take the ratio of these things, and you're going to get weights that are either gigantic or tiny. And that will do exactly the thing that we least want for our policy gradients, which is that it will increase the variance. And all that hard work we put into designing baselines and so on will be negated by the enormous variance that we'll get from those crazy importance weights. And that's a big problem for importance sampled policy gradient. We can do a few tricks. We can, you know, exploit this causality thing. So we say, well, we can basically take this product and we can put a piece of it inside the reward term and put the other piece over here, and then the rewards can go from t to capital T instead of 1 to capital T. So we can still apply that trick. But we haven't really solved the real problem, which is that we're multiplying together O of t different numbers between 0 and 1. Okay, so causality, hopefully all of you have got that picture. Now, one thing we can do at this point is we could just delete this part of the weights. That will actually change the algorithm. So you will not get the same gradient if you do that. But it turns out that if you set this part to 1, you do still get an algorithm where each gradient step will improve the policy, but for a different reason. So if you set this part to 1, you actually get a policy iteration algorithm, and we'll cover policy iteration later on in this course. But you can actually show that setting this bit to 1 will allow you to still improve your policy, but for a different reason. So the policy gradient will not be equal to the old policy gradient, but the policy will still improve. And that we'll cover later on when we talk about policy iteration. But even after doing that, you're still left with this piece, and this is still a product of O of t numbers between 0 and 1. So we're still in trouble. Okay. So here is one somewhat hand-wavy thing we can do. It'll be hand-wavy today. It'll be less hand-wavy in the second half of the course. So what we can do is we can employ kind of a first-order approximation, and you'll see why I call this a first-order approximation in a subsequent lecture, but for now I just want to tell you what it is, just so that if you have to implement it, you'll know the general idea. So this bit is still exponential in capital T, and we're very unhappy about that. So let's write the objective a little bit differently. Here's our on-policy policy gradient from before, and this on-policy policy gradient, here I wrote it in this kind of reward to go form using the Q hat from before. This on-policy policy gradient requires us to sample these SITs and AITs from the state action marginal. Remember the state action marginal from last week? Here, it doesn't actually matter that these SITs and AITs come from the same trajectory or not. They're just multiplied by the reward to go. So long as they come from the state action marginal, we're happy. Which means that we can write the off-policy policy gradient with importance weights a little bit differently. We can write it with the importance weights given by the ratio of state action marginal probabilities. So we have pi theta SIT AIT divided by pi theta prime SIT AIT divided by pi theta SIT AIT. Now this is still a bit problematic because we don't know what the state action marginals are. We just have the policy. But that doesn't stop us from factorizing this using the chain rule into a product of two terms, the policy term which we're all familiar with, and this really annoying state marginal term. We have no idea what the state marginals are, but what we can do is we can sort of embrace our ignorance there and just ignore that part. And this will actually work if theta prime is close to theta. We'll find out why this works in a subsequent lecture when we talk about advanced policy gradients, but you can actually show that when theta and theta prime are close enough to each other, the error that you get from deleting this term is small. For now, you'll have to take my word for it, but if you want to actually implement importance sampled policy gradient in practice, please don't do this. I made that mistake in one of my papers 6 years ago. Do this instead. It'll work much better. And then you'll find out why it's actually OK to do later on. Any questions about this? Yes?
Would you mind elaborating on the pi theta prime divided by pi theta? Would you mind giving an example for that?
This?
Yeah.
So this is just basically using importance sampling to estimate this quantity. So this quantity is the policy gradient whenever SIT and AIT are drawn from the state action marginal. I mean, it's true whenever they're drawn from the trajectory distribution, but because only the state action marginal actually depends on ST and AT, you can say, well, instead of putting in pi theta tau here, just put in pi theta ST-AT, because that's the only thing that depends on the state and action at time t. And once you know that, then you can do the same exact importance sampling that we did before for trajectories, only now at the level of state action marginals. Ordinarily, this wouldn't be very useful because we don't know what the state action marginals are, but if we just delete the state part, then we have two terms that we do understand. And that's something we can implement.
I guess my question is more towards implementation. Say theta, this is a deep neural network, theta is your weights, and pi theta is probably a function of all these weights coming together. And those two numbers will be their outcomes divided by each other?
Well, so the version that you would implement is this thing. So you cannot implement this part because evaluating state marginals is extremely difficult. So you would not implement this, you would just implement this.
So basically, if that's a deep neural network, that would just be the output of your neural network.
Yes, precisely. Yeah.
If we look at the KL divergence of pi theta, and or I guess pi theta prime and pi theta, would that give us the idea of whether or not?
Yes. So as sort of a preview for a lecture 4 weeks from now, yes, this thing is okay to do if the KL divergence between pi theta prime and pi theta is small. Yes.
So in the off-policy setting, the reason we're doing this is to have more samples that we can use. Is that right?
Right. So the question is, why are we doing all this stuff? The reason we're doing this is so that in the off-policy setting, as you said, we can include more samples in our sample-wise estimate. Because variance is high, which means that we want lots of samples to get a good estimate. We can't use samples from old policies unless we do something like importance sampling. So in practice, the effective number of samples we can utilize becomes much larger.
Okay. And we can only use samples that we obtained from the previous policy, theta prime.
Right. Okay, so this is a slightly more complex question. So the question for those of you that didn't hear is, are we only allowed to use samples from our own previous policies, or can we use samples from somewhere else? It depends on which formula we're talking about. So if we go back here, this thing you can do for any old policy or anybody else's policy. So any policy can be plugged in place of pi theta into this formula, and that will be correct. The bit where I killed this ratio, that does assume that pi theta was my own old policy. So there, I'm actually making that assumption, but if I don't kill that part, I can use any policy I want. If you're doing this thing and actually deleting the state probabilities, this you should only do when pi theta is a recent old policy, because you need pi theta and pi theta prime to be close together. Any other questions? Yes?
Why does it support first order approximation?
That I would ask you to save for the advanced policy gradients lecture. Okay. Now, a little bit of a practical discussion, and I want to make sure I get through this before the end of the lecture because you guys will want this for your homework. Implementing policy gradients with automatic differentiation. So this is the form of the policy gradient that is most convenient to know when you actually have to implement it. There's a lot hiding in this Q hat. That's your reward to go. But when it comes to actually coding it up, it's easy enough to decompose that out. Now, it's pretty inefficient to just calculate a bunch of grad log pi's and then calculate the sum. Don't do that because that'll be very, very slow, especially for big neural networks. But it turns out there's a very efficient, very convenient way to implement policy gradient with standard automatic differentiation packages. So what we're going to do is we're going to construct a graph in our automatic differentiation software such that the derivative of that graph is the policy gradient. Now, the graph itself will not actually be the correct reinforcement learning objective because the correct reinforcement learning objective requires interacting with the environment, but we'll set it up so that its gradient is the correct gradient. So to do that, we'll first look at the maximum likelihood equation. This is something that we're all probably very used to implementing in like TensorFlow or PyTorch. And we're going to start with an implementation of this thing and then turn it into an implementation of the policy gradient. So the gradient of the maximum likelihood, basically this is the gradient, this is the actual objective. So you implement this thing, you call like dot gradients on it, and you get this thing. So what we're going to do with policy gradient is we're going to implement a kind of a pseudo loss whose gradient is the policy gradient. So the policy gradient is this equation up here. If you actually implement this thing, notice that there's no gradient operator instead of in front of the log pi, then your autodiff package will calculate the policy gradient for you. So all you really have to do is you have to code it up so that it evaluates this quantity and then call dot gradients on it. Let's see that in pseudocode. So here is some pseudocode for maximum likelihood in TensorFlow with a bunch of function calls that I haven't defined yet, but you can use your imagination to figure out what they should be. So I calculate the logits by asking my policy to make predictions on the states. So the states is a tensor n by t by ds, where ds is the dimensionality of the state. So it's a 3D tensor, trajectories, time steps, state dimensions. The logits, this will produce a n times t by dA tensor of action logits. And then if I want to do supervised learning, if I want to do like imitation learning, like you guys had to do for homework 1, I would use, for example, for discrete actions, cross-entropy loss, where the labels are the true actions, the logits are the predictions over here. Then I do a mean reduction, so turn that into one scalar value, and then call its gradients to get the gradient, which I can climb to maximize my likelihood. So this is imitation learning with discrete actions. For continuous actions, you wouldn't use cross-entropy loss, you would use the equation for the density of a multivariate normal distribution. All right, so now let's think about how we can turn this into a policy gradient. We're going to introduce one more variable, which is q values. So this variable q values is an n times t by 1 tensor of estimated state action values. So this is computed by taking cumulative sums from the end of the trajectory to the front to calculate those rewards to go, to calculate those partial sums of total rewards. So I assume that someone already calculated those partial sums for me and placed them in a variable called q values. Now all I have to do is I have to take my negative likelihoods from this cross-entropy loss and multiply them by the q values. So that turns my original maximum likelihood objective, which is just the log pi's, into log pi times q hat. And then I just plug that into the mean reduction and calculate its gradient, and that will spit out the policy gradient for me. So this stuff up until loss equals basically implements this pseudo loss, log pi times q hat, and calling dot gradient on it turns it into the policy gradient. So these things are the q values, and this thing calculates my policy gradient for me. Does anybody have any questions about this?
Sorry, so
yes.
How do you compare the q values? Do we just assume it's given?
So these things, these q hats, these are the sums of the rewards along your trajectories from the current time step t until the end. So you would calculate these using a cumulative sum function, or you can just implement a for loop if you want. You can do this in NumPy. It really doesn't matter, because as far as the autodiff software is concerned, they're just constants.
Okay.
You do have to calculate them, though. Was there any other question?
Okay. Yep. Yeah, when you're using baselines, would you use like a moving b such that it's the average of the previous?
Right. So the question is, if you were using baselines, would you have a separate baseline for every time step? Yes, you would. Where would we plug in the baseline into this pseudocode? Anybody want to venture a suggestion? Yes?
The q bar?
Yeah, you would put the baseline into this q values. So when you calculate the q values, you would subtract out the baseline. So this code sort of assumes that it's already been done for you. And typically you could do that in a different subroutine somewhere. Okay, so I think I'm pretty much out of time. So let me briefly summarize a few high-level points for using policy gradient in practice. Remember that the policy gradient has high variance. It's not the same as supervised learning. It might look like supervised learning when you code up that pseudo loss. It's not the same. Typically, when you do policy gradient, your gradients will be noisier than you're used to. So you should use larger batches. You might consider spending a little bit more time adjusting your learning rates. Adaptive step size rules like Atom can be kind of okay-ish, but they're not going to be quite as perfect as you're used to from supervised learning. We'll learn about some policy gradient specific learning rate adjustment rules later on, but for now, what you'll be implementing in homework 2 will basically plug in the policy gradient into a standard first order optimizer. Just be a little careful, the learning rates might take a little bit more work. We'll give you some hyperparameters that will work out of the box, but when you're doing this for real, keep in mind this bit is a little bit more delicate. Brief review, and then I'll conclude. The policy gradient is an on-policy method. You can derive an off-policy variant using importance sampling. The importance weights have exponential scaling in capital T. You can ignore parts of the weights, which gives you an approximation, which for now looks like a hack, but later on we'll see that it actually makes some mathematical sense. And you can implement it with automatic differentiation software, but you have to be a little careful to make sure that you don't naively just compute all the grad log pi's and instead ask your autodiff software to do it for you. Okay, so this you'll be doing on homework 2. This should be all you need for homework 2. It'll come out either late tonight or early tomorrow morning, and please remember to finish homework 1 by 11:59 p.m. tonight. See you all on Wednesday.
I have all the prerequisites for this course.